So, dear students, welcome back to our NPTEL online certification course on analog electronic circuit. Myself Pradeep Mandal from E&EC department of IIT Kharagpur. Today's topic of discussion, it is differential amplifier in fact, today we are continuing differential amplifier, but today we will be primarily focusing on circuit analysis and maybe towards the numerical examples. So, in overall plan, we are in module 7 and under the module 7 we do have the plan of going for differential amplifier. So, in our previous lecture we have talked about basic structure and working principle of differential amplifier. Prior to that we have discussed about single ended signaling versus differential signaling. They are part of the differential amplifier background, and today we are going to discuss more on analysis of differential amplifier, specifically for two modes of operation, differential mode and common mode operation and their corresponding gain. And then we will also talk about large signal analysis, from where we can get the signal swing, possible output signal swing, and the range of DC voltage, which is referred as input common mode range. So, that is the overall plan. So, the concepts we are going to cover are the following. So, we shall start with small signal equivalent circuit of differential amplifier, both implemented by BJT as well as MOSFET, and then we shall talk about small signal analysis, specifically for differential mode of stimulus or differential mode of operation, then common mode stimulus or common mode operation, and then combined one, which is referred as generalized stimulus, and then we may have a special case which is referred as pseudo differential stimulus. And then we will be going for large signal analysis. To start with, we shall discuss about DC operating point analysis, and then we shall talk about the input DC voltage range over which devices are in proper region of operation, which is commonly known as input common mode range. And then we shall talk about the possible signal swing for a given circuit, which is referred as output signal swing. Numerical examples it will be followed after that, but I am not sure whether we will be able to cover today, but yes, this is the overall flow. Now, coming to small signal equivalent circuit of differential amplifier. So, here we do have the basic the overall model, namely we do have a differential amplifier, and then we do have the input port which is differential in nature, and the signaling we do, it is in the form of differential. Likewise, at the output, whenever we are observing the signal we are receiving in the form of differential. So, both input as well as the output port, they are differential in nature, which is referred as fully differential amplifier. And then here is the one possible implementation, the basic implementation of the differential amplifier by BJT, bipolar transistor. And then we like to go for its analysis, particularly small signal analysis. So, for small signal analysis we require small signal equivalent circuit. So, for this circuit we need to have equivalent circuit where we can drop the DC part and DC components of this current as well as the voltage, and then the linearized circuit, which is referred as small signal equivalent circuit, and there we can stimulate the circuit. So, before we go for small signal analysis, we need to know we need to get the small signal equivalent circuit of this differential amplifier. Now, in our previous lecture, we have discussed for better understanding of the circuit operation, we do have here we do have equivalent circuit. In fact, if you see this circuit, it is essentially same, except this resistor it has been splitted into two parts. One is 2 RT connected to transistor 1, and then second one is 2 RT connected to transistor 2, and we are keeping they are disconnected. If we connect the two emitters, then of course, this is same as this circuit. So, in our small signal equivalent circuit, though we will be drawing the small signal equivalent circuit of this circuit, but once we connect it, we know that we are going back to this circuit. So, then I must say that in literature, this is the circuit, it is referred as differential circuit, but for our internal analysis, we are going to analyze the circuit in this form. Okay. So, let us try to see the small signal equivalent circuit of this one. First of all, transistor 1 we can replace by its equivalent model, namely GM1 into VBE 1, and so this current is between its collector and emitter, and then we may consider the RO, collector to emitter resistance, RO1, and then we do have R pi called R pi 1, and the voltage across this R pi it is VBE 1. So, this is for transistor 1. So, likewise for transistor 2 we do have RO2, then we do have GM2 multiplied by its corresponding VBE2, this is the voltage dependent current source, and then we do have R pi of transistor 2, R pi 2, and then we do have the input terminal here. So, we call this is IN 2 and this is IN 1. These two emitter node, they are connected together, but in our analysis we like to keep this resistor splitted into two parts. One is 2 RT connected to the emitter of transistor 1, the other one it is 2 RT connected to the emitter of transistor 2, and then we do have RC1, the load resistor here, and then we do have RC2, which is the load resistor here, and then we do have output at this node, and then also we do have the output at this point. You might have observed that naming convention wise, even though we are calling this is Q1 and this is Q2, but whenever we have called this node, we call this is VO2. So, we may say that the output, one of the output we are observing here, which is named as VO2. On the other hand, the output at this node at the collector of transistor 2, we call this is VO1, and of course, this node it is AC ground. So, that is the DC node. Now, why do you call this is VO1 and VO2? That is just to take care of the polarity of the signal in differential mode. So, if I consider this input is the non-inverting input and this is the inverting input, and then the corresponding output, if we say that this is the true signal, and this is the complementary signal, and the difference of these two voltages we call say VO differential. Then with this convention we do get AD differential mode gain defined as VO1 minus VO2 divided by voltage here called V in 1 minus V in 2. So, this becomes positive. So, we are just like to have this AD positive. It is just a convention. In many of the textbook we have seen that this voltage it is considered as the non-inverting output, and this is considered as inverting output, and hence in that convention of course AD it will be negative. So, it is not so important, it is just a convention, that is all. So, with this convention, namely if I consider this is the VO1 and this is VO2, then we are getting AD is positive. So, now with this model what we can do, we can put a stimulus and then we can get the subsequent analysis to find the expression of differential mode gain. Okay. So, this is what the small signal equivalent circuit of differential amplifier realized by BJT, and here we will be giving the signal, namely we will be applying the signal here. This may be called V in 1, and the signal here it is V in 2, right. Okay. So, in summary we have drawn the clean small signal equivalent circuit here. So, just now what we discussed it is shown here. So, what we have it is out of Q1 we have drawn the small signal equivalent circuit here. So, this is for Q1. So, likewise we do have the small signal equivalent circuit for Q2, and then the 2 RT. So, tail resistors, and then the load resistors are here RC1 and RC2, and as I said that this side we like to call V out 1 output 1, and the voltage here it is VO1. On the other hand, voltage at this node at the collector of transistor 1 we call it is out 2, and the voltage here it is VO2. Note that this node it is AC ground. So, the voltage here we are considering the voltage here with respect to this AC ground itself. In fact, we may consider with respect to the common ground, but anyway for small signal analysis both this node and this node they are equal. So, they are essentially same, and then we do have the GM into VB of transistor 1, and the VB it is the voltage across this R pi 1. So, likewise we do have here VB 2. So, that is the small signal equivalent circuit, and likewise if we consider differential amplifier realized by MOSFET transistor, then we will be getting the similar kind of circuit. So, in the next slide here we do have the differential amplifier. We may consider this one or the customized one here after splitting the tail resistor into identical elements, and here again we call this is the positive side of the input, namely non-inverting input, and this side this node in 2 it is we consider negative side of the input, and with this we like to declare this is positive side of the output, and on the other hand this is negative side of the output, show that we do get the differential mode gain is whatever it is positive. Now, let us draw the small signal equivalent circuit of the differential amplifier. In fact, I already have drawn in the next slide. So, let me directly go there. Yeah. So, here we do have the small signal equivalent circuit for transistor 1 M1. So, likewise for transistor 2 we do have the small signal equivalent circuit, and then we do have RD1 here, RD2 here, and the two tail resistors, split tail resistors are there, and then this node it is AC ground, and then this side the drain node of transistor 2 we call it is out 1. On the other hand, drain node of transistor 1 we call it is out 2. Accordingly, we are declaring this is VO1 and this is VO2, and the output we consider particularly the differential output we are defining by considering VO1 minus VO2, and V in differential it is V in 1 minus V in 2, and with this definition of output polarity, output and input polarity, and this convention AD we are getting positive. So, now we like to stimulate this circuit in two modes of operation, and we like to get the expression of differential mode gain and the common mode gain for the two small signal equivalent circuits, one for BJT, another is for MOSFET. So, you may recapitulate that whenever we do have a differential amplifier, so we do have main differential amplifier containing DC sources and DC bias condition. We like to convert into small signal equivalent circuit. So, by now we do have small signal equivalent circuit for differential amplifier, and then we like to stimulate it at the input in this convention, and it is having two modes of operation. One is differential modes of operation or differential stimulus, that will help us to get the parameter AD or expression of AD in this case. And then we do have another mode of operation called common mode operation, where at both the inputs we are giving the same signal V in C, making the differential equal to 0. For this case, common mode we are making it 0. So, if we make the differential equal to 0, and whatever the differential output we are expecting, it should be 0, assuming of course A C D equals to 0, and whatever the voltage you will be getting at both the outputs are essentially the common mode output, and they are identical. So, now what we will be doing is that let us start with differential mode of stimulus for the small signal equivalent circuit obtained out of BJTs implementation. So, we do have here the small signal equivalent circuit, and we like to put the differential mode of stimulus as you can see here. So, we like to put the signal, let me use a different color. So, we like to put a differential signal here, perfectly differential, which means that here we like to put V in D by 2 and here plus V in D by 2, and both of them are with respect to a DC voltage. And once we get the small signal equivalent circuit, of course, we will be dropping this part, and then we will be considering this is AC ground. So, that is what we do have here. And so, in the small signal equivalent circuit, at this input we are applying say V in 1 equals to plus V in D by 2. So, likewise, at the other input we are applying V in 2 equals to minus V in D by 2. And in our intuitive analysis, what we have said is that if I consider say the two halves of the circuit, if I say that the emitter nodes here and emitter nodes they are disconnected. So, we can then split the circuit into two parts, and then we can observe what is the signal we are getting at this node, and we can observe the signal at this node. So, if you see this circuit, the expected signal coming at this point, it is minus V in D by 2 into the gain of this circuit, which is GM1 into RC1 divided by 1 plus GM1 into 2RT. So, this is what we are expecting at VO2. So, it is having a minus sign, and then we do have this gain. In fact, we can drop this 1, and we can as well approximate this by V in D by 2 into RC1 divided by 2RT. So, likewise, when you consider this node, and at this point whatever V out 1 we are getting, VO1 equals to minus and minus. We do have both the minuses together. So, we do have V in D by 2. So, this minus and the minus here, polarity of this amplifier, it is getting cancelled, and so this is RC 2 divided by 2 RT. And the signal coming at the emitter here, it is approximately equal to the signal we are applying at the base, because it is working as in fact it is working as the emitter follower, and so the voltage signal we are getting here, it is VE1 approximately equal to whatever the voltage we are applying there, namely V in D by 2, and then its Thevenin equivalent resistance, it is 1 by GM1 multiplied by, in parallel with 2RT, right. In fact, I should say that let me go step by step. So, if I consider only this part, and if I consider this resistance RC1, it is less than RO1, much less than RO1, which is typically the case, then we do get this relationship. And also we assume that the beta is very high. So, we consider beta is very high. So, with this approximation we obtain the V E 1 equals to V in D by 2, and then Thevenin equivalent resistance, it is 1 by G M 1, and then we do have the 2 R T. So, we do have this 2 R T, and again if I consider this resistance 1 by G M 1, it is very small compared to 2 R T. So, that is getting translated into Thevenin equivalent voltage source, it is almost remaining the same, and Thevenin equivalent resistance, it is 1 by G M 1. So, the signal we are getting here, it is V in D by 2 with a plus sign. So, likewise if you consider the other emitter transistor 2, the corresponding signal source will be getting a signal which is equals to V in D by 2 with a minus sign, and the impedance here it is approximately equal to 1 by G M 2. So, in this mode of operation, in this differential mode of operation, namely if the input 2 and input 1, if they are complementary to each other, then at this point and this point the two signals you are getting, they are complementary. Their impedances, Thevenin equivalent impedances, are also equal. So, if we connect it, if we connect it, then the signal here it will be getting 0. As a result here we can consider this is ground. In fact, before we make this connection, the signal if I draw, so before we make this connection, signal here it was like this, and on the other hand signal at this node it was having the same strength, but having opposite phase. Okay. So, this is the signal, and this signal it is shown here, and the corresponding output what we have observed at this point we do have signal which is in phase with the in 1, and it is having some decent amplification. So, we can say this is V out 1. On the other hand, signal at this point it is similar, but having opposite phase. So, this is V O 2. Now, so this was the case before we made this connection. Now, the moment we make this connection, before we make the connection, why the signal here it was low? That is because emitter of transistor 1, it was getting degenerated by 2 R T. So, only a small part of the applied signal it was appearing across this V B E. Even though we said that this voltage and this voltage they are equal, but actually this voltage it was slightly smaller than this one, and that it was the V B E. Now, and since this V B E it is only a small fraction of this applied input voltage, and hence the obtained signal at the collector, it was only I should say it was having amplification, but the corresponding amplification it was not really big. It depends on the ratio of RC 1 and 2 RT. So, same thing it was the case here at the other output. Now, the moment we make this connection, that makes this signal and this signal, they are cancelling each other, and particularly since their phases it was opposite, amplitude it was equal, and also their Thevenin equivalent resistances they are equal. So, the moment we make this connection, the signal here it completely got vanished. So, the emitter node, the combined emitter node, it becomes 0. So, the moment we make this is in fact connected, it may be having only a DC voltage, but you will not be finding any signal. So, equivalently you can say that after making this connection, it becomes AC ground, right. And once it is AC ground, then the available VBE it becomes equal to V in D by 2. So, the voltage appearing across this R pi 1, it becomes equal to V in D by 2, and once it is getting the full signal, the corresponding current here, voltage dependent current source, that also got increased. As a result, the corresponding signal here it got changed. It becomes now, so instead of this or this, it got changed to VO2 equals to minus V in D by 2 into GM1 into RC1. Why? That is because now if this node it is ground, so this circuit it becomes like same as common emitter amplifier, and we know common emitter amplifiers gain it is GM into RC. RC is the load. So, with this connection, now VO2 it got changed, and change is in magnitude of the output. So, same thing or equivalent things it happened in at the other end, namely once we make this connection, this voltage it got increased, because this the VBE2 now it becomes equal to entire V in D by 2 with a minus sign. As a result, the corresponding output here it got increased, and this output now it is so this output it becomes V in D by 2 into GM2 into RC2. So, let me clear and again summarize. What we said is that the moment we do have the signal here V in D by 2 with a positive sign polarity, and here we do have the complementary part, namely minus V in D by 2, and the moment we are making this connection to get this circuit same as the original one, then the signal here it is 0, it is 0 here. That means, this is AC ground. On the other hand, the signal coming at this point it is amplified one, but having opposite phase. So, this is VO2 and this VO2 it is equals to minus V in D by 2 into GM1 into RC1. Likewise, if you see the other side, we do have VO1 which is in phase with the differential input, and the signal here it is VO1 equals to V in D by 2 GM2 into RC2. So, the differential output VOD, which is defined as VO1 minus VO2. So, it becomes V in D by 2 into GM into RC into 2, and here we have assumed that GM1 equals to GM2 equals to GM and RC1 equals to RC2 equals to RC. So, that gives us, so this 2 and this 2 they are getting cancelled. So, that gives us the differential mode gain expression is equal to which is defined as VOD divided by V in D, this is equal to GM into RC, right. Note that our polarity convention helps us to avoid this minus sign, otherwise it is its gain, it is same as common emitter amplifier. Now, similar to this circuit, then similar to the differential amplifier using BJT, if you consider the differential amplifier realized by MOSFET transistor, we can do similar kind of analysis. So, in the next slide, we do have the small signal equivalent circuit. So, we do have the small signal equivalent circuit of the differential amplifier, and the actual circuit of course will be getting when we are making this connection. And here also, if we stimulate the circuit in perfectly in differential mode of operation, namely V in 1 equals to V in D by 2, and the signal here it is V in 2 equals to minus V in D by 2. Then before we make this connection, we are having signal here and here, but the two signals it was in opposite phase, and the gain here we obtained it was only RD divided by 2 RT, but the moment we make this connection to get the actual differential amplifier, then the corresponding output we obtain here, it is amplified version with 180 degree phase shift, and the corresponding output VO2 equals to minus V in D by 2 into GM1 into RD1. So, we do have GM1 here, and then we do have RD1. And likewise, if I consider the this output and the corresponding output, it is similar, but 180 degree phase shift. So, this is VO2 and VO2 is equal to V in D by 2 GM2 into RD2. So, again for this case the differential mode gain AD defined as VOD divided by V in D, which is equal to VO1 minus VO2 divided by V in 1 minus V in 2. So, it becomes GM into RD, where GM is, we are assuming GM1 equals to GM2 equal to GM, and RD1 equals to RD2 equals to RD. In fact, lot of common things are there across these two differential amplifier. So, so we can use the same concept in this differential amplifier to understand. So, that is why I did not go in detail of this circuit. So, now we can go for, so we have covered the differential mode of operation and we obtain the differential mode gain of the circuit. And next thing is that we can go for common mode stimulus, and then we can find the corresponding gain of the circuit called AC. And to start with, let me go with the MOSFET version first, right, and then we will be doing the analysis. Okay, before we go into that, let me take a short break and then we will come back.